All right, let's jump right in. Today, we're talking about one of the coolest and most powerful tools you'll find in any workshop, the laser cutter. We're going to follow the entire journey, all the way from a simple idea in your head to a real, physical object you can hold in your hand. Let's do it.
I mean, this is the big question, right? For any inventor, any engineer, any creator. How do you make an idea real? Well, today, we're going to answer that by diving into the world of digital fabrication, where a focused beam of light can literally bring your designs to life.
So, at its heart, what is a laser cutter? The best way to think about it is like a super-powered, computer-controlled magnifying glass. It focuses a beam of light so intensely that it becomes this incredible cutting tool. And it's not just melting things, it's a process called thermal separation, which is a fancy way of saying the material just poof, it vaporizes, disappearing cleanly right along the exact path of your design.
It's really no wonder these machines are showing up in schools and makerspaces everywhere. They are the ultimate STEAM tool, right? They smash together the precision of engineering and math with the pure creativity of art. And maybe most importantly, they teach you real-world digital fabrication skills, the kind that are absolutely crucial for so many jobs today. Okay, so here's our game plan. We're going to walk through the 5 key stages of any laser cutting project. We'll start with the tech itself, then creating the design, preparing the file, dealing with real-world physics, and finally, making it real, safely and smartly. All right, let's kick things off with the basics. Not all lasers are created equal, and the type of laser you're using really determines what you can bring to life. In most classrooms or makerspaces, you're going to be using a CO2 laser. It's the workhorse, super versatile for common stuff like wood, acrylic, and paper. You might also run into diode lasers. They're great for wood, but they have one huge limitation. They can't cut clear materials. Their light just passes right through. Then you've got the heavy hitters, fiber lasers. These are the industrial powerhouses for cutting metal, the kind of thing you'd find in a really advanced engineering lab. Okay, so you've got an idea, you know which machine you're using. Now comes the most critical step of all, creating that digital blueprint. The laser needs a very, very specific set of instructions to follow. Pay attention here because this is probably the single most important concept in laser design: vector versus raster. A vector file is like a set of GPS coordinates. It gives the laser the exact mathematical path to follow to cut out a shape. But a raster file, like a JPG or a PNG, that's just a grid of pixels. It tells the laser where to fire to create a shaded image, kind of like a printer, but it has no idea how to cut a precise outline. It's a picture, not a path. So, let me just say it again because it's that important. If you want to cut a piece out of a material, your file absolutely has to be a vector. No exceptions. That's the golden rule. It's what separates a successful project from a really frustrating afternoon. You have to give the machine a path, not a picture. Now, just having a vector file is only the beginning. Now we have to format it correctly. Essentially, we have to teach our design to speak this specific dialect that our laser cutter understands. Think of these as the 5 rules of grandeur for talking to a laser. First, you use colors to give commands, like red for cut this line and black for engrave this area. Second, any line you want to cut needs to be incredibly thin. We call it a hairline. If it's too thick, the machine sees a shape to fill in, not a line to cut. Third, every cut path has to be a closed loop, no gaps. Fourth, any text has to be converted from a font into a shape. And finally, and this is a big one, you have to delete any overlapping lines. Cutting the same spot twice is messy, it burns your material, and it's a major fire hazard.
Okay, our file is perfect. Now for the really exciting part, seeing how a flat 2D design becomes a physical 3D object. And this is where the digital world has to face the laws of physics.
And the first law of physics we need to talk about is kerf. You see, the laser beam isn't infinitely thin. It has a real-world width. As it cuts, it zaps away material, creating a tiny gap. And that gap, the kerf, means your physical piece will always be a tiny bit smaller than your digital design. Let's make that totally clear. Let's say you design a perfect 10mm square in your software. Your machine has a measured kerf of 0.2 millimeters. So what size is the piece going to be when you actually pull it out of the laser? It's going to be 9.8 millimeters. Why? Because the laser vaporized 0.1 millimeters of material from each side of the line you drew. Now, for a single piece, that might not matter at all. But if you're making parts that need to interlock, it's the difference between a snug fit and a wobbly failure.
And this right here is a core challenge for any young engineer. To get parts to fit together perfectly, you have to become a tolerance detective. You have to measure your machine's specific kerf and then adjust your digital design to compensate for it. This is where you move from just making cool shapes to real precision engineering. So, we've covered design, we've covered physics. Let's finish up with the most important part of any project, working safely and thinking like a prototyper.
Okay, this is non-negotiable. A laser cutter is not a toy, and you cannot just experiment with materials. Certain plastics, when they get zapped by a laser, release gases that are incredibly toxic. Some are even lethal, and they can destroy the machine. You always use a material that you know is 100% laser safe.
Just take a look at this list. Cutting PVC, that releases chlorine gas. ABS plastic, hydrogen cyanide. Styrofoam is literally the #1 cause of laser fires. This isn't about getting a bad cut. This is about protecting your health and the machine. The rule is simple. When in doubt, don't cut. Now, let's talk about the smart way to build. Before you ever touch your expensive final material, you start with paper. A super quick, cheap cut on paper or cardstock lets you check the most basic thing. Is the scale right? Is it the size you thought it would be? Does the shape look correct in the real world? Once the scale looks good, you move up to cardboard. This is where you test the actual engineering. Cardboard has thickness, so you can check if your interlocking slots and tabs actually fit together. This is your chance to see if you accounted for that curve correctly before you waste a nice piece of wood or acrylic. And only after you've tested on paper and then tested on cardboard do you finally move to your final material. By following this prototyping process, you're not just guessing anymore. You're creating with confidence. You're saving time, money, and a whole lot of frustration. This is the iterative design process in action. You know, this really captures the magic of the whole thing. The laser cutter is that perfect bridge between the digital world and the physical world. It's the tool that empowers anyone to take a thought, translate it into a digital language, and then make it real. So, we've walked through the whole journey from that first spark of an idea to a finished object. You now have the blueprint. You know how to think, how to design, and how to create with a laser cutter. So the only question left is, what are you going to bring to life?